Welcome back everyone. So in the last two lectures we have actually defined basic notions of Lie algebras and saw some examples. So in this lecture I will actually go through some problems, okay, which are actually somewhat very basic, and then these problems somewhat will give you good grip on the basic notions of Lie algebras. So let's begin. So the very first problem is actually very simple. It is again property of this Lie bracket. So let's say G be a Lie algebra over complex numbers. So then prove that the bracket x0 and then 0x, that should be 0 for all x in G. Okay. So I will do one of them. I will do the first bracket and then I will leave it the second bracket as exercise. So the how to prove this? So we just use the property of this 0 element of the vector space. If I add 0 plus 0, then we get 0. Okay. Because of this, now using this linearity of this brackets, if we compute x comma 0 plus 0, so that will be equal to bracket x0 plus bracket x0. On the one hand you get x comma 0, sorry, x comma 0. On the other hand you are getting 2 x comma 0. So now we are working over complex numbers. So this immediately implies x comma 0 must be 0 for all x in G. Okay. So now let us see our second problem. Again this is something to do with the Lie product. So suppose we have two elements, let us say x comma y in G, such that the bracket is non-zero. So then we want to know as vectors x and y whether they are linearly dependent or not. Because the bracket is non-zero, so one immediately gets actually x and y are linearly independent over complex numbers. So how do we prove this? We can prove by contradiction. Okay, the proof, suppose if they are actually not linearly independent, then they must be linearly dependent. So suppose not, x and y must be linearly dependent. So that will imply x will be some multiple of y for some lambda complex numbers. So that means if I compute the Lie bracket x y, then it will imply that I can replace x by lambda y and then we get lambda times y y. So the bracket x y is actually equal to lambda times y y, but we know that the bracket of x x is 0 using the skew symmetric. So that will imply this is 0. So that says the bracket of x y must be 0 if x and y are linearly dependent. So that means if you assume to begin with bracket x y is non-zero, then we must get x and y are linearly independent. So this is actually a contradiction. Okay, so let us see the third problem. This is about computing some structure constants for known Lie algebras. So let us begin with GL and C. Okay, as I said, the structure constants always depending upon the choice of the basis. So we have a natural basis for GL and C. So we will actually compute the structure constants of GL and C with respect to that natural basis EIJ. So this is actually the general linear Lie algebra over C, and we know that this EIJ where ij ranging from 1 to n, this form a basis for GL and C. Okay. So now what is the question? question is compute the structure constants for the Lie algebra GL and C with respect to this basis P. Okay, so it is actually a very simple computation. So, just I will do. So, recall this Eij is nothing but it is the n by n matrix. So, that has actually entry 1 in the ijth entry. Okay. So, this has which has entry 1 in the ijth position or the entry, and all other entries are 0. So, 0 elsewhere. So, that is the actually the matrix Eij, the it is called elementary matrix. So, now it is easy to do computation between the elementary matrix. So, matrix multiplication. So, if I take Eij and then multiply with EKL, then what we get is if j equal to k, we get EIL, otherwise we get 0. So, that means if I call this Kronecker delta jk as delta jk, then this Eij EKL is nothing but Kronecker delta jk into EIL. So, this is simple matrix multiplication. Either you can, the one best way to prove this as okay, you think this Eij as operator acting on Cn, and then just this multiplication corresponds to matrix matrix multiplication corresponds to the composition of linear maps. Using that you can easily prove this. So, this I will leave it as exercise. This is very elementary linear algebra exercise. Now, once you know how to multiply two elementary matrices, then it is not hard to compute what will be the structure constants. So, that is given by the following formula. So, if I take Eij and then compute what is this bracket. So, then it will be Eij EKL minus EKL Eij. So, then if you rewrite this using the previous formula, this is delta jk EIL minus delta IL EKJ. Okay. So, this is the structure constant that you get. So, this is this delta jk is the Kronecker delta. Okay, I hope all of you know. So, now this is easy. So, now we will actually again compute the structure constants for this another algebra, which is again very important algebra, which will appear later in our discussion. So, which is this special linear algebra SL and C. Okay. So, these are all the traceless matrices inside GL and C. So, we take this SL and C. So, this is the special linear Lie algebra over C. So, what is this? By definition, this is those A in GL and C such that the trace of A is 0. Okay. So, it is not hard to actually see that this SL and C is actually a Lie subalgebra of GL and C. So, that is some elementary calculation, I will leave it to you. So, now using the standard basis of GL and C, we can come up with a standard basis of SL and C. So, what is it? SL and C is all traceless matrices. So, for example, I can take all this Eij for all I not equal to j, they are all actually traceless matrices. Then but they do not include diagonal matrices. So, to include diagonal matrices, you just take the basis for the diagonal matrices. So, because the traceless condition says the sum of the diagonal entries must be 0. So, what we can do? We can just put 1 minus 1 in I and I plus 1 to place and then construct a basis. So, that is given by Eii minus E I plus 1 in terms of the elementary matrices. Okay, this is I ranging from 1 to up to n minus 1. So, it cannot be n. Okay. So, if you just see that it is not hard to prove, actually this is actually linearly independent. Okay, that I will just leave it as exercise. And if you count the number of elements in this set here, all these are all like off diagonal entries. So, it will be like if you count only strictly upper triangular matrices. So, that will be n into n minus 1 by 2, because the matrix of the form like this. So, this is let us say the diagonal. So, then if you take the first off diagonal position, so then you will have n minus 1 choices, then the second off diagonal you will have n minus 2 choice, you can go up to 1. So, if you add all of them 1 plus etcetera plus n minus 1, then you get n into n minus 1 by 2. So, these many choices are there for the strictly upper triangular matrices that are of the form EIJ. Okay. So, now for the lower triangular matrices you will have the again similar choices. So, you will get twice of this. So, that will be the cardinality of this. The number of EIJ will be twice n into n minus 1 by 2. And here it is easy to see that there are only n minus 1 number of matrices. So, if you count them together, this if you call this is B, so then this B, the cardinality of B is easy to see, it is n into n minus 1 by 2 times 2 plus n minus 1. So, it is actually n into n minus 1 plus n minus 1, which is n plus 1 times n minus 1, which is exactly n square minus 1. So, but it is not hard to prove, because this trace condition is one linear condition. So, that simply says the dimension of this SLN C is nothing but 1 less than the dimension of GLN. So, that is exactly n square minus 1. So, now putting together, so this B must be a basis. So, this implies this B must be a basis for this SLN C. Okay. So, this is actually a standard basis coming from the standard basis of GLN C. Okay. This is what we always refer as standard basis. So, now if you take this basis and then if you want to compute again the structure constants, so then you can see that the same formula will work for EIJ EKL. So, then now we can actually only need to compute it for this how this diagonal matrices actually help, okay, how my diagonal matrices will act on this other matrices. Okay. So, let me write it. So, the first formula is for the EIJs. So, that is easy to write. If I compute this as before, it is delta JK EIL minus delta IL EKJ. So, this formula holds as it is. So, this we are computing it for I not equal to j and k not equal to l, these indices varying from 1 to n. Okay. So, now we want to compute it for E I minus E I plus 1 E k l. So, instead of computing that what we will do, we will actually just write down it for any general diagonal matrix. So, then it is easy to derive that sub case. Okay. So, why I want to do that, because then the formula looks very pretty, which this computation will be again used later when we actually come back to this SLN C. Okay. So, that is what I want to do. So, again recall this same formula 1 can be used to compute EII EKL. Okay. But again like if you just bookkeep, because both these indices are same, I and J are same. Okay. That because of that, this formula can be reinterpreted as follows. This is exactly equal to delta IK. Now, instead of EIL, I can write EKL, there is no harm. Okay. Because if this K, if it is equal to I, then I can put K here. If it is not equal to I, then it is going to be 0. So, this is same as delta IK EIL. Okay. So, there is no issue. So, now this the second term will be similar to that delta IL EKL. Okay. So, this is just a small modification of the formula 1 for this special case. Now, using this it is easy to compute what will happen to any diagonal matrix. Let us say D is a diagonal matrix. So, diagonal matrix we write it this way, diagonal A1 etcetera AN, or in terms of the basis if you write, this is exactly A1 E11 plus etcetera plus AN EAN. So, when I say basis, the basis for the set of all diagonal matrices. So, it is written this way. Okay. So, now if you compute D with EKL, then it is easy computation. Then what we get? We get exactly summation AI EII EKL, okay, for I ranging from 1 to n. So, now again using this earlier formula, you can see that because this I varies from 1 to n. So, when this I hits k, then it will survive. So, it will give me AK EKK EKL, EKK EKL will be just this term EKL. Okay. So, this is going to be EKL, and then if you just if I hits L. So, note that this k is not equal to L. Okay. We are computing the structure constant for the elements of this SLNC. So, EKL to begin with k should be not equal to L. So, then because k not equal to L, this I can take value both k and L. So, when I takes value L, then this is exactly AL EKL. Okay. So, this says the bracket D EKL is nothing but AK minus AL times EKL. Okay. So, this is the formula that we get for all D. Okay. So, this is actually very important formula. So, we will actually reinterpret this term that appear here, okay, in terms of what is called projections. Okay. So, for any this diagonal matrix, we can easily define what is called ith coordinate projection, because this is written as A1 E11 plus etcetera AN ENN. So, ith coordinate we can take it to be the coefficient of EII. So, in that sense this AK will be the kth coordinate projection, L will be AL will be Lth coordinate projection. So, basically it is different between those two projections. Okay. This is one way to think about this equality. We will come back to this later. Okay. This is actually very important observation later that will be used in the theory of semi-simple Lie algebras. Okay. So, now I guess we got somewhat more comfortable with some of these computing structure constants. Again later when I do this classification of smaller dimension Lie algebras, again we will actually compute structure constants with respect to some special basis when we take dimension 2 or dimension 3 and so on. Okay. So, now I want to move on. So, these are all about basic Lie algebras and structure constants. I also introduced some of these notions, other notions called homomorphisms, derivations and so on. So, I want to actually do some problems related to that. Okay. So, here is the fifth problem. So, we define what is called this adjoint map. So, let us recall, which is a very important map. Okay. So, adjoint map. So, what is this adjoint map? You have this Lie algebra G, and then this map is defined from G to GL of G. Okay. So, recall GL of G by definition as a vector space, okay, as a set it is endomorphism of G. So, this is the set of all C linear maps from G to G. Okay. So, what is the dimension of this GL of G? The dimension of GL of G is nothing but the dimension of G square. Okay. So, I stopped using this C, but it is understood, okay, we are working over C always. So, now this is the map that we are defining, this adjoint map. What it does? It takes an element x to what is called add x. So, what is this add x? Where this add x is a map again from G to G. So, this is a C linear map. Okay. So, that is easy to check, given by add x of y is nothing but bracket x y for all y in G. Okay. So, this is this particular map that we are talking about, which is just a linear map. We also checked this is actually a derivation. Okay. So, that is something we already checked. So, we checked add x is a derivation for each x in G. So, in particularly this add adjoint map is indeed mapping to set of all derivations of G. Okay. So, which we denoted by D or G. Okay. This is the set of all derivations of G. So, this is sitting inside GLG. Okay. So, now the question is this add map, okay, this we have defined from G to GLG. So, we also have a Lie algebra structure on GLG given by the commutator bracket. Okay. We have a composition of maps that makes GL of G as or the endomorphism of G as associative algebra. So, once you know that this is an associative algebra, then commutator bracket will actually give you the Lie algebra structure on this. Okay. That is what we denoted by GLG. So, now what is the question? Question is prove that this add map is actually Lie algebra homomorphism. Okay. So, for that we need to check the following. So, linearity is very clear. Okay. So, I will leave it to you to check, it is easy to see add is C linear map, okay, that I am not going to check. So, the only thing that we need to check, so the claim is this is actually obeys the Lie structure, that means add of bracket x y should be equal to bracket of this add x add y. But what is bracket of add x add y? That is nothing but add x composition add y minus add y composition add x. So, this is the definition of commutator inside this GLG. Okay. Add x y is this, this is what we need to prove. So, this we need to prove as maps, but if we just rewrite everything, we will see that this is nothing but just a Jacobi identity. Okay. So, let us do it. So, let us rewrite one by one. Okay. So, what is on the left hand side? So, the left hand side you have add bracket x y defined on Z. Okay. So, then what it is? It is nothing but bracket x y Z. Okay. Because this is one element and then you are taking the bracket with Z. So, now what is on the right hand side? Right hand side the first equation, let us say. So, this is let us say 1, this is let us say 2. So, then right hand side 1 is nothing but add x composition add y applied on Z. So, if you just reveal it, this is first you are applying the add y map. So, you get y z and then you have to compose it with that x. So, then you apply x. Okay. Similarly, right hand side 2. So, that is nothing but add y composition add x on z. So, that nothing but first apply x z, then apply y. Okay. So, then what do we need to do? We need to prove that if we call this is 1, this is 2, this is 3, then if you go back we have to prove 1 is equal to 2 minus 3. Okay. So, we need to prove 1 is equal to 2 minus 3. But let us look at it. Okay. So, let us take the first one. The first one is nothing but bracket x y z. Okay. So, now let us use Jacobi identity. To use Jacobi identity, it is better to rewrite this way bracket z bracket x y. This is first we have used what is called skew symmetric. So, now if you rewrite this, this is exactly minus z x y minus x z y, because this is already derivation. So, this is Jacobi identity, or we are using that add z is derivation. Okay. So, then this is now if you rewrite, what do you get? You get for example, from here bracket x y z. So, I am switching this. So, then this will become plus bracket y z x. So, then if you rewrite again x y z minus minus y x z. Okay. So, that is what we wanted to prove now. So, this minus this should be this. This is the first term x y z and then y x z. So, we proved bracket x y z is this. Okay. So, it is basically rewriting the Jacobi identity in a different way, and that proves that add x y is nothing but add x composition add y minus add y composition add x. Okay. So, this says this map adjoint map is actually a Lie algebra homomorphism from G to GLG. So, it is a very important fact. Okay. It will be repeatedly used. I would say that you better check yourself at least once. Okay. So, now let us get back to what is called this derivations. Okay. So, I want to just clarify one thing. Okay. So, we actually defined the many objects, okay, in the last 2 lectures. So, just for some clarification, I want to actually recall what are all the things we did. So, first we defined, okay, there is this bigger class called algebra over C. So, here we are not assuming anything about the product. For example, the product may not be commutative, may not be associative, nothing. Okay. Only thing is there should be some compatible condition between the product that comes from the ring structure and the scalar multiplication. So, this is basically a vector space, on top of it, it has a product, okay, and that product and the scalar multiplication that comes from the vector space should have some compatibility condition. Okay, that is all. So, now this actually includes what is called this associative algebra. What is associative algebra? The product should satisfy the associative law. So, if you call the product is x y, then x y z should be equal to x y times z. So, this should be true. Okay. This is the associativity law. And here we saw another algebra called Lie algebra. Lie algebra, again it is highly non-commutative, non-associative algebra. Okay. I urge you to check the Jacobi identity is not equivalent to associative law. Okay. So, it is actually one can come up with some characterization when that Lie product will become associative. I will add it in the problem sheet. Okay. So, this is different structure. So, this is non-commutative, non-associative algebra structure. Okay. So, this is what we have seen. Again here you can go further down, we can actually talk about what is commutative associative algebra. Okay. That is also somewhat very interesting class that one can study in algebra. But here if you go down and then add commutativity, then it becomes trivial. Okay. So, there is nothing like commutative Lie algebra. So, commutative Lie algebras are nothing but vector spaces. Okay. So, they are not that interesting, not interesting. Okay. This is what we have done so far. So, when we talk about derivation, we actually define derivations on algebras. Okay. So, that is actually somewhat better way to do, because all this calculation works there in the algebra setting. Okay. So, here is the problem that is related to derivation. You start with an algebra over C. That means we have a product, that is all. We have a product from A cross A to A. The product often denoted by just xy. Then the compatibility condition should be there between the scalar multiplication and the multiplication. So, it should satisfy this property for all alpha in C, xy in C, xy in A. So, now because of this I will be able to define derivation on A. Okay. So, because what is derivation? Derivation on A is a C linear map that satisfies Leibniz rule. So, what is that? If you take the product delta A B, then you get A delta B plus delta A B. Okay. This is the usual rule that you see in calculus. Okay. But here we are writing it for any algebra capital A. So, a derivation delta is a C linear map satisfying this. Okay. So, this is all I defined already, I am just trying to recall. So, now we also define what is called this derivation A. These derivations of A are nothing but the set of all derivations. Okay. Set of all derivations of A, which sits inside endomorphism of A. Okay. But we will see in a minute. We already know that endomorphism of A has this product that is given by composition. So, this GL of A is nothing but the Lie algebra structure on this endomorphism of A. So, now this derivation A is actually subspace of GL of A. So, then the natural question is that whether this derivation A is Lie algebra or not, Lie subalgebra or not. So, that is the case. So, one can prove that derivation A is a Lie subalgebra of GLA. Okay. So, this is the plainly computation. So, let me do it for you. So, here I will not check that derivation A is a vector space, vector subspace of GL of A. I will only check whenever you take two elements D comma E inside this derivation of A. So, then if you take this bracket which is defined in GLA, which is the commutator bracket, D composition E minus E composition D, that should be again a derivation. Okay, that is the thing we need to prove. So, let us try to verify it. So, it is basically a computation. So, let us again do it like what is on the left hand side, and then right hand side, and then we will just match. So, if you just compute what is on the left hand side. So, this is we need to prove that this is actually a derivation. Okay, to prove that derivation, what we need to do, we compute this d e acting on a b. So, then we need to prove this is actually giving me d e of a times b minus d e sorry a times bracket d e of b. Okay. So, this is the thing you need to actually check. So, let us do this calculation. So, if you compute what is on the left side, okay, so the left side computation that we are doing. So, then what is d e of a b? So, that is decomposition E of a b minus E composition D of a b. Okay. So, then let us compute this. So, then you get D E a b plus A e b minus E d a b plus A d b. So, then if you just bring it in, so this term like 1 and then this term is like a 2. So, then you get d e a b, okay, plus E a d b again plus d a e b plus A d e b. Okay. Similarly, minus E d a b plus d a e b and then minus E a d b minus A E a d b. So, now you can see that there are natural cancellations. So, this get cancelled with this and then this get cancelled with this. Okay. So, then if you just cancel them and then group it, then what you get? So, you get d e of a b plus A d e b minus E d a b minus A e d b. Okay, this is one side, left hand side. So, now let us compute what we required on the right side, okay, and then see what happens. Okay. So, the right hand side. So, we need to compute the first term, let us call this is first term, this is the second term and then we will add the first term bracket d e acting on A on and then product with B. So, this is nothing but, so d e minus E d acting on A and then B, which is d of E a and then B minus E of d a times B. Okay. Similarly, A times d e bracket d e acting on B. Okay, then you get A times d of E of B Okay, let us not jump, let us just do it step by step. So, dE minus EB acting on B. Okay. So, then what you get? A dE acting on B is equal to A times d of E of B minus A times E of D of B. Okay. So, this is 1, this is 2. So, now what is 1 minus 2? That is what we need to compute now. 1 minus 2. So, 1 minus 2 is equal to sorry, not this is 1, this is so this is 1. So, you get d of E of B plus okay, A E of D of B and then minus E of D of A B and then minus A D of E of B. Okay. So, you can see whether it matches with this. So, this is the LH side. So, this is the RHS side. Okay. Let us see matching or happening or not. So, this is let us say the first term and this is matching with this, okay, d E of E B, and then the second term A E of D of B. Okay, some sign is missing. So, that term is here. Okay. And then yeah, this term is fine, E of D of A B, and then this is minus. Okay, this sign I guess some problem. Okay, so it is 1 minus 2. So, yeah, maybe I missed some sign here. We need to do, oh sorry, this is actually the derivation. So, the derivation should have plus here, okay. dE of AB should, okay, this is not the definition, okay, sorry, this is correct. Where is the definition? The definition of so, this is the definition of bracket dE, that is fine. What we need to check? Yeah, so this is the term 1 and this is the term 2, this is the term 1, this is the term 2. So, basically we need to add that, okay. So, we should not subtract. So, this is adding. So, if you add it, then the terms are matching. So, then this must be plus and this must be minus, okay. So, in the right hand side, yeah. So, this term with comes with minus A of E of D of B. So, that is comes with minus here and then here again it is plus. So, it is all matching. So, this is the third term, the third term is here. Okay. So, that proves LHS equal to RHS. Okay. So, that means this bracket D is again a derivation for all D comma E in derivations of it. Okay. So, this completes the proof. I will just leave one exercise and then stop. Okay. So, this is again called Leibniz rule or generalized stability rule, because it can be obtained from whatever the rule that I already told. So, here is the exercise. So, again start with an algebra over C. So, then take delta to be a derivation. So, that is a linear map satisfying the rule delta of A B equal to A delta of B plus delta of A B, delta of A B. Okay. So, now what I want you to prove that this if you compose n number of time and act it on x y, then it has this formula, very nice formula. So, this formula you must have seen in calculus, the similar formula works here also. And choose var delta r of x delta of n minus r of y, and this is true for all x y and a. Okay. So, this is just done by induction. I will leave this as exercise, because I do not want to do another computation. We will stop here. Okay. I will continue with other important basic notions like subalgebras, ideals, homomorphisms, and then this isomorphism theorems and so on in the next class. I will stop here. Thanks.